Hello again, students, and welcome to this lecture, which will introduce you briefly to the column of chapters in the handbook that treats the supply chains of the different types of biomasses and biofuels. To begin with, let's open up chapter 0300, which is the introductory chapter, and go down to the planning aspects and to a table that is present down here in this section. This table might seem a little bit complicated, so before we go into it and look at what it really means, let's first look at the text that is below this table, and that is this text. So if we read this text, you will understand that this table that we will soon look at is by no means definite, but it serves only to illustrate some very important aspects of things. Now, in the table, there are three different types of final treatments that come into the table, and that is biochemical treatment of the fuel, it's direct combustion of the fuel, and it is thermochemical conversion of the fuel, like gasification, pyrolysis, or liquefaction. It's important to have some fundamental concepts clear before we look at the table. And to do that, let us look at this text that very, very briefly describes a few things that are typical for the different processes. One important aspect is that the production of livestock manure and or, for example, sewage sludge from a city wastewater treatment plant or sludge production by regional industry, these may be trusted to have a reasonably constant supply of feed, so that there is a fairly constant flow of substrate to a biochemical treatment plant. Now, that means that the biochemical treatment plant will have to accommodate this flow. The flow will not be variable to any great extent. At the same time, it is important to realize that the substrates suitable for biochemical treatment, they are suitable for that treatment because they are easily digestible. And that means that they cannot be stored without being deteriorated. If you use biochemical treatment, or if you have access to a flow of a substrate suitable for biochemical treatment, then that plant will have to be a base plant, a base load plant, running all the time, accommodating the whole flow and working all year round, basically. The substrate cannot easily be stored. It's also important to understand that this kind of biochemical treatment processes will be able to accommodate a certain amount of wet crops or crop residues as additives to the substrate. As you remember from the resources lecture, that since agricultural residues are seasonal, digestion plant, or the fermentation plant for that matter, has to be able to accommodate the amounts of wet agricultural residues that may be produced during, let's say, June or July or August, during harvesting months, while at the same time the biochemical treatment plant must be able to operate only using the constant flow of sludge or manure or whatever is available during the other months when harvest is not about. Looking then at the direct combustion as a way of extracting the energy and utilizing the fuel, the direct combustion process is the only one in which 100% of the fuel energy is released in one single operation. That means that it will usually lead to high temperatures in the combustion chamber. These high temperatures will also lead to ash melting if the ash has a low melting point. Many different crops and agricultural residues, as pointed out in the ash properties appendix to this handbook, and has already been pointed out in the fundamental properties lecture, and will again be mentioned in the process lecture. Many crops have low ash melting temperatures, and depending on how the combustion chamber has been designed, this may lead to operational problems that may be more or less severe. In contrast to that, woody fuels typically will have high ash melting points unless they are too contaminated by soil and other extrinsic contaminants that may have entered into the fuel fraction during the supply chain. So woody fuels or woody biomass will generally have a high ash melting point, and that renders it very suitable for direct combustion. The dimensioning and the design of the combustion chamber can also be such as to accommodate molten ash. This is only a question of designing and dimensioning the combustion chamber. But then it also has to be remembered that many crops will also exhibit quite high chlorine contents and also significant contents of sulfur. Again, in contrast to woody fuels or woody biomass, which would typically have very low contents of these elements. So, typically, direct combustion needs a fuel that has a sufficiently high heating value to provide a high temperature. But on the other hand, it's easiest to run a direct combustion process if the fuel ash does not melt to too high an extent. Now, combustion chambers can be designed to handle dry fuels or wet fuels or moist fuels. And typically, we can say that a dry fuel is a fuel where the moisture content is like 20% or less. A moist fuel is a fuel where the moisture content is about 20 and up to 40%. And a wet fuel is a fuel where the moisture content exceeds about 40%. The different designs will be apparent in the construction of the walls of the combustion chamber. And a combustion chamber designed to handle a dry fuel will not easily be able to handle a wet fuel or even a moist fuel. So the combustion chamber can be designed for wet, moist or dry fuels, and this holds true for woody fuels as well as for herbaceous fuels. But the main constraint is, of course, that the fuel must be combustible, so that the fuel itself shall be autocombustible. It shall be possible for the fuel to burn without any extra energy. This constraint obviously effectively excludes all types of sludges where the water content may well exceed 80 or 90%. So they will not be combustible and it will not be an alternative to put a wet sludge into a combustion chamber unless you have a base fuel so that the combustion is already running. Looking then at thermochemical conversion processes, be it gasification or liquefaction or pyrolysis, the aim and the idea is to retain the energy in a product fuel. In gasification, the product fuel is a gas. In liquefaction, the product fuel is basically a liquid, and in pyrolysis this can be set and adjusted so that the resulting product fuel is either a liquid or a solid fuel. But common to them all is that the idea with the process is to retain as much as possible of the original feedstock energy in the product fuel. Hence, what you want to do is to run the process at the lowest possible temperature to obtain a complete conversion of the feedstock into the product fuel, or as a complete conversion as you can reach, but to keep the process temperature as low as possible. Because to keep the process temperature, what you do is that you oxidize a little bit of the fuel, of the feedstock. So you consume a bit of the feedstock to maintain the process temperature. This in turn leads to that the input, the feedstock, must not be too wet. Because if the feedstock is too wet, then first your heating value is low, and second, you have to use a lot of the energy only to boil off water, and that will render your thermochemical conversion process very, very inefficient. So there's a demand in thermochemical conversion that the moisture content of the fuel is low. And when I say low, I mean less than 20%, or at the very least less than 30% moisture content. Having said this, let's now look at this table. You will notice that the rows, there are 3 rows. There is 1 row for fermentation and anaerobic digestion, 1 for direct combustion, 1 for thermochemical conversion. Each row is split into 2 sub-rows. The upper sub-row will contain comments about the fuel economy and availability. The lower sub-row will contain comments about the fuel suitability for storage. The fuels treated are putrescibles, like manure, sludge, etc., and they are put in contrast to solid materials, wet solid materials, and dry solid materials. And the solid materials are in turn split into herbaceous and woody. With woody, I also include waste fractions. You will realize that this is only solid waste fractions from municipal waste and not the organic waste fraction from municipal waste. The organic waste fraction from municipal waste would go into manure and sludge, etc., because it is basically biodegradable. Whereas, for example, demolition wood or old bookshelves, furniture of non-painted material, clothes, which is basically cotton, would go into the waste fractions, etc. The turquoise boxes are there to indicate that the material, the fuel and the process are possible to combine and will give a reasonably good result. The green ones are there to indicate that the material, the fuel, is well suited for the process, whereas the blank boxes are to indicate that this material is not well suited for the process. So, looking then at this table, you will see that it says in the comment boxes that for manure and sludge, etc., the amount available as well as the price will be sensitive to the long-term market. What that means is that certainly every year the production will be more or less constant. But if, for example, the population of cattle decreases because of market conditions, then the total availability of manure will obviously go down. It also points out that putrescibles are not suitable for storage. But the green boxes indicate that putrescibles are best suited for fermentation and anaerobic digestion. So the supply chain of these has to take into account that they cannot be stored, basically, but the supply chain, especially for a fermentation process with putrescible agricultural wastes such as manure or sewage sludge, will only be long-term variable. You can plan for it to be reasonably stable. However, if you want to introduce herbaceous material into your fermentation or anaerobic digestion process, you must be aware that especially if the herbaceous material is from annual crops, then the amounts available and the price you have to pay for them will be sensitive to weather and be very variable from one year to the next year. This was pointed out already in the lecture about resources. In contrast to that, woody materials and waste fractions will both certainly be variable. The price will be variable depending on the long-term market. But with woody fractions as well as with waste fractions from household, we're talking longer time for the variations. They will not be so very variable from one year to the next year, whereas there may be a long-term trend. In case wood is wet, it can be stored for some time, not too long. The deterioration of wood will consume order of magnitude 1 in a very good, well-planned storage, up to about 5% of the total mass every month. So in a poorly planned store or with inadequate storage on the whole, you may lose 5% of your stored wood material every month. The heat released may lead to autoignition. Wet wood can be stored for some time, but it's not the best thing to do. For herbaceous material, the storage properties are worse. Herbaceous material has less lignin, it has a higher content of proteins and fats and lipids which are easily digestible. So herbaceous material will deteriorate at a higher rate than wood. So even though herbaceous wet material and wet wood can be mixed and fired in direct combustion in the same boiler, you will have to treat the two fuels separately all the way up until the boiler, unless you want the easily digestible herbaceous material infect the woody material so that both degrade simultaneously at a very high rate. You will want to keep these two separate all the way, and the supply chain has to be planned according to that. If the materials are dried, then the situation becomes different, and the handling becomes very much easier. In this case, both resources may be stored, but there is still the problem with the herbaceous biomass that it contains higher amounts of chlorine and sulfur, that it typically has a lower ash melting point than the woody materials. And that renders the herbaceous material less suitable for direct combustion than the woody materials. Wet materials are not very well suited for thermochemical conversion, as was already pointed out. The efficiency in the thermochemical conversion processes will suffer from a high moisture content. So to be suitable for thermochemical conversion, the materials have to be dry. The water content should be at the very, very highest 30% and preferably less than 20%. If they are, then both herbaceous material and woody biomass are well suited for thermochemical conversion processes. The supply chain has to take the storage possibilities into account. It has to take the storage properties of the individual biomass into account. If the supply chain can guarantee and provide a dry material, then the type of process and the type of plant, or the possibilities, the potential types of plants becomes different than if the supply chain cannot guarantee a dry material, etc. There is an intercoupling between the process and the supply chain, which is very important to understand. And having now introduced this table, we shall start to go into looking at the supply chain, the unit operations that occur during the supply chain, and how the supply chain can be organized for the different types of fuels. Looking then at the supply chains and starting with harvesting as one of the main unit operations, and first looking into woody biomass, one might say that we should first distinguish between different types of forest operations. There are significant differences between how a clear cut is done and what happens during a selective cut, including, of course, thinning operations as selective cuts. As you see from this table, there is a difference in the fuel fraction property and also in the amounts, depending on which type of operation we are talking about, if it's a clear cut, a selective cut final, or a selective cut thinning. At final cuts, provided the primary product to be extracted is actually timber for sawing, then the main cost for the operation may perhaps be attributed to the timber itself, and in that case the marginal cost for the fuel fraction can be kept very low. If the amount of fuel fraction is then big enough, and of course provided a close eye is kept on the quality, then this will be the most economic way to produce slash or brash from forest operations. However, the total cost will of course be affected by the terrain, for example if cable logging is needed or if machine and mechanized logging can be used throughout. And there will also be traditions coming in, so that forestry is done in different ways in different parts of Europe because of history. So that will also affect not only the cost but also the technology applied. Going further down this chapter to text section 3.2, you will also remember that there is a lignocellulosic production from agriculture. You might want to recall the maps that we looked at previously in the lecture about resources, the maps over Europe, showing the access or the potential of forest residues but also showing the potential of prunings and residues from agricultural activities, residues of lignocellulosic biomass, that is. As said in the introduction to this section, in some European countries, especially in the Mediterranean area, there is agricultural woody biomass residues that have a greater potential than forest residues, like for instance in Italy or in Spain. So you should not neglect the potential of lignocellulose from agricultural activities. Considering these residues, you should distinguish between prunings, which have a fairly constant annual production but may only be low amounts, and uprooting residues, which are obtained at the end of the commercial life of the plantation. In both cases, there will be residues available, but the prunings will be a constant supply on an annual basis, even though the amounts may be low, whereas the uprooting residues will be available only in long intervals, but then there will be very huge amounts available that need to be handled. As for prunings, it is obvious that with dense plantations and narrow passages, in combination with a rather thin material to be harvested, the machinery used to collect this material are different from those used in forestry. The important thing, though, is to point out that such machines are actually available on the market. So you do have access to mechanical means to extract the prunings and turn them into a useful fuel product. Another type of lignocellulosic biomass that can be produced from agricultural activities is the so-called short rotation forestry. For SRF, the biomass is harvested only at 1 to 3 years of age, and the trees will be only a few centimeters in diameter. For this, then, the machinery, the harvester, will basically resemble a combine harvester for agricultural use, but of course it will be more robust and dimensioned to handle a more coarse and tough material. Typically, the harvester and chipper are combined, as shown in this picture, so that you produce the chips in one operation together with the harvest. As a contrast, medium rotation copies allows the trees to grow for a longer time, so that their diameter may be like 10 to 20 or 25 centimeters. That means that the harvesting machine must be more of a forest harvester than an agricultural harvester. So the machinery and the mechanization used in this type of agricultural lignocellulose plantations resembles more that of normal forestry than of agriculture. Now, talking about lignocellulose, it is very easy that people forget that also industrial residues and household waste will contain quite a lot of lignocellulose. There will be byproducts from industrial processes, there will be wooden waste from households, and this type of materials also need to be collected and used in the energy system. Turning our eyes now into herbaceous biomass instead, let's go down and have a look at the harvesting and collection of herbaceous biomass. There is one major difference as comes to the harvesting, and that is that unlike woody biomass, herbaceous biomass is harvested in locations that are easily reachable and where existing and standing plants usually do not limit the operation because the field is dedicated for growing a certain crop. Hence, Mechanization is very easy. So therefore, the harvesting of agricultural biomass is typically highly mechanized, and there is a number of different types of machines and possibilities available. But there is also one other difference. While forest operations typically occur on an annual basis, more or less all year round, then since the harvesting of herbaceous biomass is an agricultural activity, then it's only performed in limited time windows, depending on the plant type. For example, maize residues should be collected at the very most 30 to 40 days after the grain has been harvested. With herbaceous biomass, you have specific times to access it, and it can only be harvested at these times. That being said, there are several different possibilities to collect herbaceous biomass, and some indicative operations can be seen in this picture. You will notice that the harvested material can either be bales, or it can be chopped, or it can be pellets. But in all cases, as indicated from this picture, there are machines available that can do the harvesting and the chopping, or the harvesting and the baling, or the harvesting and the pelletizing, basically in one operation. So this is a major difference from forest handling, from the handling of forest fuels, that in these cases, for herbaceous biomass, there are machines available to do a pre-treatment of also the fuel fraction. In the text sections filling out this chapter, you will find discussions about these different harvesting technologies and about the different process chains, their advantages and their disadvantages. So let's have a look at the patricibles. Looking at the table of contents, you will realize that in very many cases the material is more or less liquid. This holds true for some of the manure and droppings from cattle, and it definitely holds true for anything that we call sludge. A sludge is basically a water suspension of solid material holding at the very least 60 or up to 95% water. Parts of the municipal solid waste will also be very sludge-like. So for these materials, they are very often liquid or semi-liquid. So the collection or the harvesting of these materials is obviously very different from different cases. You will pump these materials to a great extent, but you do not want to pump them over longer distances. So a local handling at the place where the materials are available is essential for the patricibles. That means that the scales become very different. There will be everything from small farm scales up to the scale of a large city water treatment plant. So the scales of handling and the scales of anaerobic digesters or fermenters becomes very, very different for these. Therefore, it is very hard to say anything general about the collection or harvesting of patricibles. For municipal wastes, though, we may say some things, and that is treated in the text section about collection systems. Now, household waste collection obviously becomes very different depending on if we are talking an area with apartment houses or an area with freestanding single-family houses. But generally, you will have to collect the municipal solid waste in both situations, and there will be different collection systems. A major difference is who shall take the responsibility for separating the waste into different fractions. In apartment houses, you may have a waste chute where people just put a bag of waste outside their apartment and it drops down into a bag, a collection bag, down at the basement. In this case, there is no possibility for the household to separate different fractions, but it all ends up in the same bag. And that main bag, the big bag, is collected by the municipality at regular intervals. And then the municipality will have to do the sorting afterwards. There is the other possibility, which is that the individual household, the tenant, brings down their waste to the basement in separate bags and puts it in separate bags or containers down at the basement. For freestanding houses, the curbside service is the most common. That means that the single household has one or several garbage bins and put them outside the house at regular interval, where they are collected and emptied into a collection vehicle. In this case, the household has the full responsibility to separate the waste, just as the case where the tenant carries his own waste or her own waste downstairs to the basement in the apartment house. So it's a question of where one wants to put the responsibility, and that will affect the collection system. We will have good reason to come back to the collection system and how they affect the whole supply chain in a while, but let's first go back to the top again and have a look at transport of the material. Looking into the transport of biomass and of biofuel, it is important to remember that transports can be basically of three different types. First, we have the short distance transports in direct connection with the harvesting. These may sometimes require special vehicles, but they would only be short ways from the harvesting in the field, for example, or in the forest to the roadside. Then there is the second transport, which may be a road transport of the raw biomass, the raw biomass itself. It can be wet, it can be very voluminous, but it has to be transported, or it may have to be transported to an upgrading site or to a site for comminution. And then finally we have the transport of the biofuel itself from an intermediate store or from an upgrading plant to the final user, the energy plant. These three types of transports may require quite different vehicles, and they may put different demands on the logistics and planning. But in most cases, the limiting factor for the transport and what affects the economy is the bulk density of the material, or the bulk energy density of the material. The bulk energy density is the amount of energy stored per cubic meter of loose material as on the transport vehicle. Each and every vehicle or carrier is characterized by two limiting factors. First, there is a maximum load, a maximum amount of tons that can be loaded. And second, there is a maximum volume, a maximum amount of cubic meters that can be loaded. In case the bulk density of the material is low, so there's only a few kilos or a few tons per cubic meter, then typically what happens in the carrier is that the volume is full, but the weight limit is not reached. With the high bulk density, the opposite situation is true. The weight limit might be reached before the volume is actually full. In case of biomass and biofuel, the situation is very often that the transport is volume limited, so that the total amount of tons is not full in the vehicles, but the volume is full. And that means that the transport will become expensive. So increasing the bulk density is a crucial factor to improve the transport economy. Now this can only be done for the road transport. It cannot be done for the transport in the field or at the harvesting site, because there we are handling the raw biomass. So let's have a look at the situation for forest biomass, and we go down to the text section dealing with the logistics and the transport aspects. In the case of forestry, the brash or the slash is often extracted using a forwarder. This is a special vehicle constructed to work in forest terrain, and it's a very odd vehicle that cannot be used for anything basically else than transports in the terrain. So forwarders are used for the transport from the felling site up to the roadside, but then different vehicles are used. For forest fuels, there will also be a very good illustration in figure 14 in chapter 3.1 that indicates the differences in bulk densities. So what this picture illustrates is the same total amount of mass with slash or brash, with trees and tree sections with branches still on them, chipped material, bundled or baled material, and actually round wood. This is the stems, the trunks, and nothing else. And you will realize that when you want to transport the slash, then you will need several cars to carry it, whereas if you could compact it into bundles, then you could do the same thing with only one car. So the handling of the material and the unit operations, compaction, comminution, fragmenting, will affect the transport economy radically. The same thing basically holds true also for herbaceous biomass, where you will look at this picture. We looked at this picture before, but now I will point out especially the right-hand side column, where we have bales that are treated and stored, where we have again bales produced by a field baler. We can have the chopped material, which is typically a very low density material, and we can also have pellets, so that we pelletize, for example, the straw already during harvesting operation. These different types of materials will have quite different bulk densities, and obviously they will also exhibit very different transport economy for the road transport. So the choice of harvesting method and the choice of treatment of the material in the field, whether a baler already at the harvesting or open air drying with subsequent baling, both results in bales which are very much more economical from a transport point of view than ever loose material. As for the putrescibles, the situation is quite different, because they would typically be in water suspension, so they are basically pumpable, and in case there is a need for a road transport, it would be in a tanker car, like any liquid chemicals. For waste fractions, there are a number of different types of vehicles available. Common to these systems that handle waste and waste fractions, especially from households and in cities, is that many of the vehicles, whether they are loaded from the rear loaders or side loaders or whatever, they are very often equipped with an internal compressor to compress the material and hence to increase the bulk density and to get a better economy than they would if they were not compressing the material. This is something that is unique for garbage vehicles, for vehicles designed for the collection of municipal waste. And unfortunately, such vehicles are not available for herbaceous biomass or for woody biomass. But there is also a third solution, which is quite common in garbage collecting systems, and that is with container carrying trucks, so that the garbage is collected in containers and the containers are transported on normal trucks. This is also the most common for wood chips or for herbaceous biomass. The material may be chopped or chipped, stored in containers, and the containers are then transported. So container carrying cars have a major role to play in the supply of biomass and biofuels. The next unit operation to be looked at is drying, which is also very important in the system. The water content of biomass or biofuel is one determining factor for its heating value, and we will talk a little bit about that looking at text section 3002C, which deals with drying. The equation given in the middle of this page, this equation, is general. This is the lower heating value of any substance with a certain ash content and a certain water content. The lower heating value, Q net, equals the net heating value, the lower heating value, of the dry ash-free substance, which is indicated by the subscript DAF, dry ash-free. The heating value for the dry ash-free substance is then multiplied with 1 minus the ash content. So 1 minus the ash content is the amount of ash-free substance. And then it is also multiplied with 1 minus the water content, which is equal to the dry material. So the net heating value, the lower heating value for the dry ash-free substance, is multiplied by the fraction of ash-free material, and then it is multiplied by the fraction of dry material. But then there is a second term. From that we subtract 2.4 multiplied with the fraction of water in the fuel. That means that the water content of the fuel comes in twice. First it comes in the first term, where the amount of dry material is determined by this parenthesis. And then it comes in a second time, multiplied by 2.4 and subtracted from the first value. So you will realize that the water content is of huge importance for the heating value of the fuel. You will also remember what was said in the introductory lecture about fundamental properties of biomass, where it was pointed out that the lignin content is one determining factor for the heating value. And the higher the lignin content, basically the higher the heating value. That is what is illustrated in the table just above this formula, where the Q net DAF values, the reference values for the dry ash-free substance, are given for a few different types of biomasses. You notice how the woody biomasses are the ones that have the highest heat value, Q net DAF, except for oil-rich agricultural byproducts, where only rapeseed refuse is indicated in this table. But the same thing applies to, for example, olive refuse. Oil-rich seeds or oil-rich materials will typically have very, very high heating values for their ash-free and dry substance. Second are woody biomasses with their high lignin, agri-industrial residues like press cakes, which will again contain a bit of oil, may have high heating values, whereas, for example, cotton spills, which are almost pure cellulose, will have very low heating values, dry ash-free. Agro-fuels such as herbaceous biomass, like cannery grass or straw, hay, they will typically have fairly low heating values. So the values in this table, they are only indicative values. They only give rough intervals, but they indicate the order of magnitude of the heating values for the dry and ash-free substances of a number of different biomasses. Going back to the equation for the heating value, you will notice the importance of ash, that the fraction of ash is another determining factor for the heating value. Now, there are two different types of ashes. There is the intrinsic ash, which is the ash that naturally occurs in the plant and is composed by the minerals and the inorganic materials that are needed for the survival and the life of the plant, for its growth. These include sulfur, chlorine, nitrogen, phosphorus, but also a number of different metals and minerals such as calcium, sodium, potassium, and a number of others. But then there is also the extrinsic ash. The extrinsic ash is the ash that is added through the logistics and the handling of the material. If, for example, the material is stored on ground and a tractor drives over it before it is collected from the ground and put into a container, then it will be contaminated with soil, and that adds to the extrinsic ash. The same thing applies if the material is transported in open containers on a dry dirt road, so that road dust accumulates in the container. That's again logistic ash or extrinsic ash added through the logistic and handling. Very often the logistic ashes are the same order of magnitude or even more than the intrinsic ash. So the ash composition and the ash content of the biomass as such is most often not representative of the biofuel that is finally delivered to the plant. But the ash in the biofuel finally delivered to the energy plant is most often determined by the logistics and by the handling throughout the supply chain. Therefore, it is important to keep a close eye on the entrepreneurs and the handling steps Looking now at the drying itself. Drying can mainly be accomplished in 3 different ways. The open air drying is the cheapest and simplest method. To acquire a good open air drying, the biomass needs to be exposed both to sun and wind, but at the same time it should be protected from heavy rain. So storing biomass outdoors in covered windrows or in covered piles that are not compacted but porous, so that wind gets access to it, oriented in such a way that sun can shine onto them, and storing it like that for a number of months can bring down the water content from the 50 to 60% or even higher in fresh biomass down to approximately 40%, 30 to 40%. This is the cheapest and best method for drying. With very wet biomass, such as bark from a sawmill, pressing or centrifuging, which are both mechanical dewatering processes, can be applied. Typically, a mechanical dewatering process cannot achieve lower water contents than approximately 50%. So it is only applicable to very wet materials. But it is cheaper than forced drying, and it is very much faster than open air drying. So mechanical dewatering can in some cases have a role to fill. The most expensive method by far is forced drying. Forced drying is to add heat and add ventilation air to the biomass, to heat up and vaporize the water, and then to carry the water vapor away from the material. Forced drying can only be applied in case there is economy enough to carry it. It's very expensive, and it's also quite dangerous, because even low temperature heating of biomass material may, if the material is contaminated, lead to ignition. So avoid forced drying both for economic reasons and for risk reasons as far as you can. And try to plan the supply chain so that open air drying can be accomplished. Basically, the limit with open air drying is, however, set by the fiber saturation moisture content. And if you want to get below the fiber saturation moisture content, then you will have to rely upon forced drying. Now, this would then be applicable in cases where you need to get below approximately 20% by weight of moisture. And that is only in cases where fuel conversion, thermochemical fuel conversion, is the process. So in case of gasification, liquefaction, or torrefaction, or pyrolysis as a whole, then forced drying may be the only alternative to bring the water content down to the levels that are demanded by the process. You will also realize that in the case of biochemical conversion, such as anaerobic digestion or fermentation, then the microorganisms need the water. So typically what is called dry or high density digestion or high density fermentation, they would occur with water contents that still have to be more than 60%. And in many cases you would prefer to have a pumpable material for these processes, so you would go for water contents that are well above 90%, or at the very least well above 85%. So for biochemical conversion, drying is not a problem. The philosophy of just-in-time deliveries is not applicable to biomass for energy supply chains. This has two main reasons. The first is that the energy supply system in society has to have an extremely high reliability. It cannot be accepted that the supply of base energy for society suddenly breaks just because there is a lack of deliveries. The second reason has been touched upon especially in the case of herbaceous biomass, where the biomass itself is available only on a seasonal basis during harvesting periods. So the availability of the biomass can be very variable over the year, depending on what is the base for the energy system. Hence, there will always be a need of storage to be included in the biomass supply chain, and we shall now have a look at the storage of biomass. Storing is then an unavoidable step in any solid biomass supply chain. The problems associated with storing do mainly come back to the very fundamental fact that biomass is degradable. Now, any biomass can be degraded by bacteria and fungi, basically. Even lignin is finally degraded. And as soon as biomass is stored, especially if it is stored in comminuted or fragmented form, so that the cells are opened and the cell liquid, which contains nutrients and also a lot of sugars, is exposed to the microorganisms, then the degradation starts. Degradation starts immediately, the moment that biomass is exposed to spores of mold, spores of rot fungi, or to bacteria. Basically, this occurs the moment the biomass is harvested. But if it is put in a pile where the central parts of the pile provide food because the cell liquid is exposed, and they provide shelter because it's wind protected, then what happens is that microorganisms establish in there. They will create their own environment. By their own biological activity, temperature will rise, the moisture content will adjust according to temperature, and they will build up their own environment and live in there. They will successively spread through the pile. During the life of these microorganisms, what they do is that they feed on the material that is stored. And this is shown in table 03022, which gives some typical values of dry matter losses in storing herbaceous biomass. Now, the values in this table will concern only round bales, large round bales, but they will indicate what happens during storage. You will see in the two right-hand side columns how the storage time, up to 9 months or 12 to 18 months, will affect the total range of dry matter losses, depending on whether the biomass is in an enclosed barn, only under roof but still on the soil, if it's covered, or if it is padded or elevated so that it is not in direct contact with the soil, or if it is uncovered and directly stored on the ground. You will notice that in the lower right corner there might be, in 18 months' time, up to 50% of the dry matter lost from a large round bale. You are advised to do the following calculation by yourself, but if you assume that a round bale has a weight of 500 kilos, that the material stored is straw with a heating value of 12 megajoules per kilo, and then during 12 months it loses up to 50% of its weight. So 250 kilos of straw with a heating value 12 megajoules per kilo are consumed during 12 months. Then the mean heating power that is developed inside that round bale is 100 watt. So imagine you put into the bale a 100 watt electrical heating element with no thermostat, and you just leave it in there. From the beginning, when the material is wet, there is no problem. But then the material around the heating element dries, and there is a risk of ignition because there is no thermostat to this element. What happens in reality is that the process starts by biological activity, microorganisms establishing, and some of these microorganisms are thermophilic, so they will survive up to 80 or 90 or maybe even 100 degrees Celsius. But when the temperature becomes as high as 80 to 100 degrees Celsius, what happens is that chemical reactions will start to take over. So even if the microorganisms die at these temperatures, simple chemical reactions will start to take over, and they will again release energy. So the released power will then increase from 100 watts maybe to 200 or 300 watts. The temperature may continue to rise and auto-ignition may take place. So do that calculation. Try to estimate what is the average heating power developed under worst conditions. And then you will realize how important it is from a safety point of view that dry matter losses are avoided during storage. And you will see from this table some indicative values on how big they may be in case the storage of wet herbaceous biomass is inappropriate. There is also another table in the course literature, but that is in the chapter about lignocellulose, and that is this table, table number 4. This table indicates the limits demanded or set by Swedish insurance companies for the storage of lignocellulosic material. The maximum height of the piles is given in meters, and the maximum storage time is given in months. And you will see that if the material is not compacted, so it's loose packing, then the allowable times are generally a bit longer. The reason for this is that to avoid a buildup of heat in the piles, and this holds true also for herbaceous material, what you need is to cool the material, and you can only cool the material by allowing air to pass through it. So with a loose packing, the pile is permeable, and the heat developed will cause a chimney effect that pulls cold air into the pile and maintains a lower temperature in the pile than if the material is packed. You will have to be very, very careful when storing biological material, because it does deteriorate. There is a risk for autoignition, and you will lose material during storage. And these losses can be quite big. In the case of lignocellulose stored in an inappropriate way, you may lose about 5% every month. That's a significant loss which will affect the total economy of the supply chain. It will also affect the quality of the fuel finally available in the stored pile and the fuel that you are able to deliver. You will have to be very, very careful during storing and plan the storage very carefully so as to allow for low storage heights and the shortest possible storage times. But you will not be able to avoid storage totally. With municipal wastes, the storage is typically in plastic covers. So you would enclose the solid organic fraction in plastic covers so that it is sealed. That will make it possible to store organic waste for some time, but only for a short period of time. The packaging will resemble that used in agriculture for silage. And then, finally, for putrescibles, storing is out of question. You will not be able to store putrescible materials at all, because the reason they are putrescibles and are suitable for the biochemical conversion processes is that they are so easily degradable, and you will not be able to stop that degradation. Solid organic waste fractions can be stored if stored in enclosed and sealed plastics. Putrescibles cannot be stored. Herbaceous biomass and woody biomass has to be stored. For the product fuels resulting from any type of conversion, be it thermochemical conversion or be it biochemical conversion or pyrolysis, the storage situation is different. Whether a gas is produced in a thermochemical process or via a biochemical process, then the product gas will contain the main part of the chlorine content of the fuel, and that chlorine will be present in the form of hydrochloric acid, basically in gas form. The gas will also be saturated with water vapor. If the gas is then stored in a tank where the temperature is allowed to drop below the dew point so that water starts to condense, the hydrochloric acid will be found in water solution together with other corrosive components. So the condensate will be very corrosive. There will also be other acidic gas components, such as carbon dioxide, present in the gas. Storing of a product gas, whether it's landfill gas, raw biogas from an anaerobic digester, or it's gas from a thermochemical gasifier, may lead to corrosion problems, and the tank and the materials in the tank and tubing must be chosen accordingly. For liquid fuels, some of them, such as fatty acid methyl esters, have been after-treated so as to stabilize them, whereas some of the liquid biofuels, such as cold-pressed oils or pyrolysis oil, will also contain corrosive components and water. So the storage of these oils may also be a bit problematic. For cold-pressed oils and also for pyrolysis oil, it must also be remembered that the oil is by no means pure. It will contain a lot of different hydrocarbons, some of which may be easily oxidized and basically may solidify, partly in contact with oxygen, but partly also because temperature is low. For the storage of bio-oils that have not been chemically stabilized afterwards, after the production, but the simple bio-oils, such as pyrolysis oil or cold-pressed oils, it is highly recommended that the tanks are continuously agitated and they are also heated, so as to keep the oil flowing and homogeneous. For solid product fuels, such as charcoal after a full pyrolysis, a high temperature pyrolysis, or the charcoal produced after torrefaction, the storage becomes a little bit simpler, because these materials, the charcoal, may be regarded as basically biologically inert. However, it is not chemically inert. So if there is a contact with a catalytically active metal, such as nickel or iron, these metals may catalyze the combustion reactions, and also charcoal may self-ignite, just like fossil coal may self-ignite. Unfortunately, these metals, nickel, iron, chromium, are also components in stainless steel. So you will have to take very good care about the storage tanks and the enclosures in which the material is stored. So we have now talked about a number of different unit operations, and time has come to look into comminution or fragmenting of the material. Comminution or fragmentation of biomass will, on the one hand, as we talked about when discussing transport properties, increase the bulk density and hence improve the transport economy. But then on the other hand, as we just talked about when discussing storage, it will also open up the cells and expose the cell liquid to microorganisms. And as we just said, that will make life very much more comfortable for these microorganisms. Therefore, even though you might think that fragmenting the material as early as possible is a good idea to improve transport economy, the general advice instead is to postpone fragmentation until the last possible moment. Actually, the very best is if fragmentation can be delayed all the way until the material is fed into the conveyor belt or into the screw that is feeding the dayhopper, just prior to the boiler or gasifier or pyrolyzer or whatever reactor you have. If this can be organized, if the fragmentation can be delayed until that moment, just prior to feeding the dayhopper, then different fractions can also be mixed in the input stream to the fragmenter, so that the fragmentation is also a homogenization of the material, and both unit operations, fragmentation and homogenization with mixing, both take place in the same unit. However, if there is the slightest risk that the mixed and fragmented material might need to be stored for more than one or a few days, then any mixing of material should be avoided. The reason for this is that the microorganisms will establish immediately, and they will happily consume whatever has been exposed via the cell liquid. Now, if the material is mixed, then in the cell liquid there will be easily degradable sugars, and the colony of microorganisms will grow very rapidly, so that also such biomass that is in itself not easily degradable will be, let's say, infected, and hence the overall degradation of the overall fuel mixture will be much faster than if the assortments had been kept separate. For the fragmentation, there are mainly 4 different types of equipment that are used. Chippers are typically using sharp tools, let's call them knives, to cut the material into pieces. Shredders are, on the other hand, using blunt tools and tears the material into pieces. In a mill, the material is basically disintegrated by rapid impact of, for example, hammers or blunt tools, whereas in a crusher the impact is very slow. The material is compressed and breaks under compression. This means that the different tools and the different types of equipment will have quite different properties, and it will be sensitive to different things. A chipper using sharp tools will be very sensitive to any contaminants like stones coming in with the material. Since the chipper aims to cut the material, it will be a combination of cutting and shearing that disintegrates the material, and the energy requirement for comminution in a chipper will be to a great extent depending on the shear strength of the material chipped. Reasonably wet biomass or moist biomass can well be chipped, whereas, for example, dry wood is very difficult to chip because it has a very strong resistance to the cutting operation, whereas moist wood, such as 30% moisture content, is easy to chip with a low energy requirement. A shredder uses blunt tools that pass between each other, and the material is sheared and torn into long pieces. This type of fragmenting is fairly insensitive to contaminants, as long as stones or pieces of metal are not too big. Shredders are preferably used when we are talking like waste materials, household waste or industrial waste, like also demolition wood, depending of course on the total power of the motors running the shredder. Mills, in these applications most commonly a hammer mill, are working with a rapid impact onto the particles, and as the hammers hit the particles break. That means that the particles have to be reasonably brittle. They can be hard. They should not be tensile, because if a tensile particle is hit at a high speed with a hammer, then the only thing that happens is that the particle is deformed. So the material needs to be brittle. Mills like the hammer mill are mainly used when you are aiming for very small particles, such as, for example, pulverized fuel firing. A crusher works with a slow impact. For example, in a ball mill or a rod mill, such as are used for coal milling or coke milling. For biomass applications, the material needs to be brittle to be crushed in a crusher. And that means that, for example, wood pellets that are dry and needs to be broken up into small particles, or dry demolition wood, can also be disintegrated in a crusher. The crusher is very often insensitive to contaminants, and hence nails or metal objects that might be present in, for example, demolition wood would be not a great problem in a crusher, whereas in, for example, a chipper, it would destroy the edges of the knives. The 4 different types of fragmenters have different roles to fill for different types of biomass. And then there is also an ongoing development of new technologies whereby the fragmenting would mainly be done by slow shearing. This seems to be an operation which might produce more isometric, less needle-like particles with less of a ragged surface than the 4 types of fragmenters we have just discussed. If that is so, if the material becomes more rounded and with a more smooth surface than it does from chippers, shredders, mills or crushers, then that would make the subsequent conveying of the material into the reactor very much easier. So, continuing through the supply chain and the unit operations, we have now arrived at compaction. Now, compaction can either be done as an initial operation, most often in conjunction with harvesting, such as shown in picture 03021, where baling and pelletizing may both be performed in the field as at the same time when herbaceous biomass is harvested. Or the compaction may also be applied to forest residues, as is exemplified in table 03012 and also in text further down in that chapter. For forest slash, the bundles will be more porous and less compact than with bales of agricultural residues, such as straw, and hence the microbiological activity in bundles of forest slash is not at all as severe as it was in the examples we saw before about what could happen in round bales of straw. You may also recall the picture 030114 about the loading capacities of trucks that we saw before, and that will also explain to you why bundling will affect the transport economy in a very positive way. While these types of compaction mainly aim to reduce the transport cost for the first road transport, that is, from roadside at the harvesting site to some kind of intermediate storage or upgrading facility, then the second type of compaction will rather aim at the final user. This second type of compaction is mainly pelletizing and briquetting, and in both these cases the bulk density is raised significantly, but there are also other advantages with pelletizing and briquetting. The main features of these two products, pellets and briquettes, are that they are mainly produced from sawmill residues, that is sawdust, cutter shavings and the like, so they are basically pure stem wood. Both products, pellets as shown in this picture and briquettes as shown in this picture, will have reasonably uniform shape, but they will also have a reasonably uniform density, moisture content and composition, because they will usually be produced using industrial residues. The uniformity will make such upgraded fuels most suitable for small-scale applications, such as small heating systems with a thermal power less than approximately 1 megawatt. This will also apply to the agricultural pellets that may be produced during harvest of a specific crop. The fact that there is a specific crop being harvested and that the pellets are produced immediately means that the raw material is uniform, the moisture content is uniform, the handling and hence the amount of extrinsic ash is also uniform. So again, the uniformity of these upgraded fuels is the crucial thing. And these are the things, the factors, that makes these fuels most suitable in the smaller scale, less than approximately 1 megawatt. In such small systems, as will be discussed basically in the next lecture, which deals with processes, non-uniform fuels will inevitably lead to bad environmental performance. The smaller the scale of the heating system or the application where the energy is extracted, the more important becomes the uniformity of the fuel. A small thermal unit cannot compensate variations in fuel quality, as can a large unit where the control system is advanced. I would say that we have now covered the main part of the unit operations that are effective in a biomass supply chain and in a biofuel supply chain. We have talked about the harvesting, transport, drying, comminution, the storage and the compaction. What we have not talked specifically about is homogenization, though the importance of homogenization was mentioned in the context of compaction. And we have not talked about conveying. Now, the conveying and the dosing of a solid and inhomogeneous material into a reactor, be that reactor a combustor or be it a gasifier or a pyrolyzer, is a problem in itself. And you will realize that the conveying and the dosing is very closely connected to the shape, the ruggedness of the surface, and the density of the particles. But it is also very closely connected to the uniformity of the material, i.e. to its heating value. Because most conveyors, be it a screw or a conveyor belt or a cell feeder, will dose volume. They will not dose mass. Hence, the conveying system is definitely worth considering when you are planning a system. But it will be a case-by-case study that has to be applied to your own application and your own situation. So it's very difficult to say anything very general about conveying, except for the repose angles and the consideration about the inclination of conveyor belts and screws that are mentioned in the text section about conveying. So I think this concludes basically this lecture. See you again some other day.